We're going to begin our study of calculus with a review of the concept of a function. This is probably something you're familiar with from your algebra or maybe pre-calculus courses, but it's going to be absolutely central to everything we do in calculus. And so we'll begin by reviewing how it works. Here's the plan for our review of functions. We'll begin by taking a look at the concept of change and the role that variables play in studying change. We'll then turn to some notation and vocabulary for talking about functions. And finally, we will recall the idea of a graph of a function. Let's begin by taking a look at change, its role in calculus, and how variables can be used to keep track of things that are changing. Calculus is, if you had to define it in a single phrase, the branch of math devoted to studying change. In other words, anytime you're going to be studying something that is changing, you're probably going to use calculus. But to do this, in order to apply mathematical methods from calculus to things that are changing, the changes have to be controlled. Another way to put that is they can't be completely random. If something is changing in a completely random way, it's very hard to study that in any systematic way using math or really anything else. Now, in calculus, at least at the level we're going to be studying it here, the changes we're going to be looking at are those that involve two variables, two things that are capable of changing. One of these variables is one that we control directly. And then the other one is a variable that changes based in a sort of indirect way on the variable that we do control. So let's think about an example to make this a little more concrete. So imagine you're doing a science experiment and you want to test how the temperature of water affects its ability to dissolve salt. Very typical sort of thing you might do, say, in a chemistry class. Well, here's how you might set this up. Take a bunch of samples of the same amount of water, but heat them to different temperatures. Then pour salt into each sample and see how much salt dissolves in each sample of water at each temperature. So notice here, there are two variables involved. One of them is the temperature of the different samples of water. And that's the one we control directly. We decide as we are setting up the experiment what temperature each sample of water is going to be. We call this the independent variable of the experiment because it is independent of anything except what we decide. So it depends only on how we decide to set things up. The other variable involved here is what's called the solubility of the salt in the water. In other words, how much salt will dissolve in the water or in each sample of water. So this changes as well, but it changes because of the changes we make to the temperature of the water in each sample. So we aren't changing the solubility directly, we're changing it by changing the temperatures. We call this the dependent variable of the experiment because its value for each sample of water depends on what we set the temperature to be, what we set the independent variable to be for that water sample. So those are the two variables involved in this experiment. Now, let's think about what we might do mathematically with the results we get from our experiment. So it's very common, if you do the sort of thing we just described in, say, a chemistry lab, to represent your results using maybe a table. It might look something like this. We would have a column with the different temperatures that we've set the water to. Maybe that's measured in degrees Celsius. And then in another column, we'll have the solubility, here measured in grams per 100 milliliters, of the salt in each sample of water at each temperature. So here might be some results that we obtain. This would be what we do when we actually run the experiment. And notice here in this table that for each temperature, there is a particular value for the solubility, right? So if your temperature of your water is 10 degrees Celsius, for example, that gives you a solubility of 35.72. And the arrangement in the table makes that easy to see. So what we can say here is that the solubility is a function of the temperature. In other words, if you pick a temperature, given what you now know from your table, you can figure out the associated solubility based on that temperature. That's all you need to know. We say in that case that solubility of salt in the water is a function of the temperature. And that leads us then to the general idea of a function. So we're going to get much more abstract now. Let's say we have two quantities, two things we can assign numbers to. We'll call them X and Y. And we'll say that Y is a function of X if each X value is associated with a Y value. And there's another requirement: no X value is associated with more than one Y value. So what this means is that once you pick your value for X, you're sort of automatically forced into a particular value for Y by this association established by the function. Now, maybe it's obvious, but just in case it's not, I'll point out that X here is the independent variable of our function. That's the one we control, and then Y is playing the role here of the dependent variable, the one whose value depends on what we choose for X. And this is a fairly common notational convention. Typically, if you're talking about a function, you often use X for the independent variable letter and Y for the dependent variable letter. Not always. Sometimes there might be good reasons to use other letters, but these are sort of standard ones to use if you don't have anything better. It is worth keeping in mind, though, that especially in calculus, you will often see other letters associated with the independent variable and the dependent variable of a function. One type of example we'll see fairly often involves functions whose independent variable is time. And in those cases, we will almost always use the letter T for the independent variable letter, T for time, of course. Or to give another example, we'll see down the road some geometry problems involving an area of a circle, and we'll treat the area as a function of the radius using the familiar formula for the area of a circle. So in that case, we'll often use R for our independent variable letter, right? R for radius, and it's common to use then uppercase A for the dependent variable, which would be area in this case. So just be aware that in calculus, you will often see various letters used associated with whatever they represent, and you'll want to pay attention to that. It will help you to remember what it is you're talking about when you use these letters. Let's turn now to some notation and vocabulary that we can use to talk about mathematical functions. The first thing we're going to need are some names for functions if we're going to talk about them and apply calculus tools to them. Now, just like in pretty much anything in math, you can use whatever symbol you want as the name of a function, as long as you're clear about what you mean when you use it. So you want to make sure that your audience will know what that symbol means and that you're using it to talk about a function. And we'll see this later. In calculus, we often think of almost every symbol that shows up in setting up a problem as a name for a function. So there's going to be a lot of different function symbols floating around for us down the road. But again, in general, unless you have some good reason to use something else, there are certain standard symbols that we use. And in the case of a function, our standard go-to default letter that we will use to refer to these things is F. F for function, of course. You might also see other letters near F in the alphabet, like G and H, and you might see uppercase letters as well, like uppercase F or uppercase G used as function names. One thing to keep in mind is that in mathematical contexts, an uppercase letter and a lowercase version of the same letter are different symbols. So for example, if you see lowercase f and uppercase F written out in a statement of a problem, they probably mean different things there, and you'll want to pay attention to the differences in their meanings. And of course, you're also familiar with certain functions that have their own special names and special symbols because they get used so frequently. So one example that you are surely acquainted with is the sine function from trigonometry. And we use the symbol, the sign abbreviation SIN for that. There's the natural logarithm function, one we'll use quite frequently in calculus, for which we have the symbol ln as a name for that function, and so on. Once we have names for functions, we can start building new types of symbols up from those to talk about other things we want to talk about. So again, let's think of our standard setup here. We've got a function, we'll call it f, and it involves two variables. The independent variable we'll call x, the dependent variable we will call y. And then we can talk about the value of y that our function relates to a particular value of x. And the symbol we'll use for that is the letter f, the function symbol, with x in parentheses after it. And we read that, if we're reading out loud, as f of x. Or if you want to be a little more verbose, you can call it the value of f at x. And f of x here refers to a number. It's a value of the variable y, the dependent variable of our function, once we pick a value for x. So finding that, figuring out what value f of x has once we choose a value for x, we call evaluating our function f at x. Another bit of vocabulary that you'll see in this connection and that we will use fairly often is in terms of inputs and outputs. So we'll sometimes say that a value we assign to x, the independent variable of our function, is an input into f, and the associated value of y, or the value of f of x, is the output of the function for that input. Let's look at an example to see what's involved in evaluating a function. One way we can use our function notation, this f of x notation, is it gives us a way to describe functions by telling us a kind of rule or formula for turning an input to the function into an output. And these kinds of formulas we sometimes call analytical representations of functions. Here's a simple example. We might say that f of x is equal to x squared. In other words, once you pick a value for x, to get the associated value of your dependent variable, y or whatever, you square whatever you assign to x. So the value of f at x is x squared. Another way to put that is if y is our dependent variable letter, we can say that y is going to be equal to x squared for whatever value of x we might choose. So let's say that we decide to give x the value 4. We can assign x any value we want. It's the independent variable. Its value is up to us. We're going to choose to give it the value 4. And we want to know the associated value of y, our dependent variable. So what we're going to do is take 4, plug it in for x into our defining expression for our function, right? Y will be equal to f of 4. And remember, f of x is equal to x squared. So f of 4 is equal to 4 squared. And of course, 4 squared is 16. So that gives us the value of f of 4. We have successfully evaluated our function f at 4. It can also happen that the input expression to our function includes a variable. So let's stick with our example where f of x is equal to x squared. Instead of replacing x with a constant like 4, we can replace it with an expression that includes a variable. So to take a really simple example, let's say we want to know what f of t is, where t is some other variable that maybe measures something else other than x. Well, that would just be t squared. We're just assigning x the value t. Or we could ask, what is f of 2x? And now we can go back to our equation that defines our function, and wherever we have x, we'll replace it with 2x. And then we can do whatever arithmetic or algebra we want to do. Raising 2x to the power 2 can be written as 4x squared if we want. So symbolically, all that's happening here is a kind of substitution. whatever appears in parentheses after the function symbol goes in the place of the independent variable in the expression that defines our function. Here, that expression is x squared. Let's wrap this brief review of functions up with a look at graphs of functions, because we'll rely on those quite a bit in calculus. We talked briefly and looked at an example just a moment ago of an analytical representation of a function, a kind of formula using algebraic expressions or other kinds of expressions like that, that tells us how our function turns an input into an output. And these can be quite useful because they're very precise. Given what we know from algebra and things like that, we know exactly how to use these kinds of formulas when we're given one. But it can also help to have other tools for working with functions, because sometimes we might want to look at sort of general patterns or trends in the values of a function. And so we might, in some sense, want to look at many different function values at once. And so there are other ways to represent functions that allow us to do that a little more easily. One that we'll use a lot in calculus is what's called a graphical representation of a function, or sometimes we just say a graph of a function. So let's look at how this works and how it connects up with variables. When we're drawing graphs of functions, we usually use what's called the Cartesian or rectangular coordinate plane. You're familiar with this from algebra. This is our coordinate plane that has two axes, a horizontal axis and a vertical axis. And when we're drawing the graph of a function, we typically use the horizontal axis to keep track of values of our independent variable. So that's often x, so we often refer to this as the x-axis. And then the vertical axis is used to keep track of values of the dependent variable. So we often use the letter y for that, and so we call this often the y-axis. So this is the familiar xy coordinate plane that you know and love from your study of algebra. Once we have our coordinate plane, we can start seeing how to assign points to the graph of a function. So when we have a function, it's going to take a particular x value and associate it with a particular y value. And we can record that in the graph by plotting the point that has that x value as its x coordinate and that y value as its y coordinate. So go back to our example from earlier. We use the function defined analytically by the equation f of x equals x squared. For this function, if x equals 2, y is going to be equal to 4. So in the graph of the function, we will see among the other points on the graph, the point 2, 4. And then we can graph the entire function by drawing the graph of the equation y equals f of x. So we can pick different values of x, find the associated values of y, get an ordered pair out of that, plot that point. And if we do that for every value of x and the associated value of y, we get the entire graph of the function. Here's a quick example. Let's say we'll change our example slightly. Let's say that our function is defined by this equation here, where f of x is equal to x squared plus 1. So if we want to draw the graph of this function, it will be the graph of all the points whose coordinates satisfy the equation y equals x squared plus 1. This is what it will look like. Notice that I've plotted a few particular points here and labeled them with our ordered pairs. And if you take any of those x coordinates, 1, 2, or 3, and assign x to have that value in our defining equation for our function, you will get 2, 5, or 10 as your value of f of x or y. And if you do that for every possible value of x, you'll get the parabola that you see here. So that is the graph of this function that we're calling f. Now, in calculus, like I said, functions are going to play an absolutely critical role. They will be the main objects of study in calculus. And that's because, as we saw with our little water solubility example a moment ago, when we're talking about changes in quantities that we're studying, we use functions most of the time to represent those changes and to keep track of how things are changing. Now, we're not going to have time here in this calculus course to study how functions work in complete detail. That would take an entire school year. In fact, if you've taken a pre-calculus course, that's really what pre-calculus was all about. How functions work, how to use them, and what they can do for us. Some of the things that we would go into detail about if we had the time to do it, or if this were a pre-calculus course, would be things like the domains and ranges of functions, how to combine functions to make new functions, how to transform functions to make new functions, certain kinds of functions that can be grouped into categories that have common features or common properties, like polynomial functions, rational functions, exponential functions, trigonometric functions, and so on. And that list could be extended quite a bit. So that would take a long time. We're going to take for granted here in calculus that you are familiar with this stuff. So we're going to count on you having studied these things earlier and being at least somewhat familiar with them from your algebra and pre-calculus courses. This course, which is a version of AP Calculus AB, takes for granted that you're familiar with functions and their behaviors. Of course, as we're going through things, anytime we need to review something critical about functions, we can take the time to do that.